Hey kiddos, on this tutorial I want to show you how to answer several of, if not all of the questions on our Skinny from pages 106 to 107. So we're continuing with our discussion of interpretation of confidence intervals and just how to talk about them. We're not necessarily mathematically constructing anything just yet. That is in our near future. So let's begin. I'm going to just type out, as I would in class, some of the answers and talk to you about each one. So number 9, we're talking about a sampling distribution of X bar. So sampling distribution is, there goes our bell. In a sampling distribution, it's a distribution that accounts for every possible sample, and it plots it into one distribution. So if your samples are of size 5 and you're talking to 5 people from a population, a sampling distribution is taking every possible combination, which is tons and tons of samples of size 5, and putting it into one distribution. So our question is, why is the interval of numbers between X bar plus or minus 2 standard deviations called a 95% confidence interval? Why do we call it that? So let's begin by remembering what the empirical rule says. So let's say, according to the empirical rule, 95% of our data will fall within 2 standard deviations of the mean. So just to separate it, I'm going to bold this guy out. Do it in purple because I do like this in purple. So remember, if it was, a 68% confidence interval, it's going to be plus or minus 1 standard deviation of the mean. And if it's a 99.7% confidence interval, it's going to be plus or minus 3 standard deviations of the mean. So I need us to just recall that 68, 95, 99.7 rule, which is also known as the empirical rule. On number 10, they want us to sketch a 90% confidence interval, and this is going to take me a long minute to explain, because there are some important numbers we need, and you guys are not used to finding these numbers. So I'm going to assume we know nothing here, and I want us to begin by drawing our normal curve. So I'm going to go over here where I have some more room. So hopefully you remember that. Then we're going to be 90% confident. So if I'm 90% confident, that means this is my mean, right? This is my standard deviation. We're going to standardize it because, let's go back, the word is standard normal. So if it's standardized, my mean is going to be 0 and my standard deviation is going to be 1. And I only want 90% confidence. So I want 90% of my data. So the thing we're missing though, and this is the part that's going to hurt your brain, is what is this number right here and right here? So there's good news. This is a symmetrical distribution. So both of those little blue clouds are going to contain the same number, but one is going to be negative because it's to the left of 0, and one's going to be positive. I personally prefer to find the negative one first, and I'm going to show you how we do that. This is a percentile. This is a percentile. And I want to know, when I plug into my calculator, to the left of that cloud, what percent is right there. So if the whole curve is 100%, let's go to my calculator. The whole curve is 100. I'm extracting out 90, because there's 90% in the middle. That leaves me with 10%. But 10% is in each of the tails. So really on the left side, half of 10 is 5%. So holy cow. We're going to go to our calculator and we're going to do inverse norm. And you're going to get to the point where you memorize these numbers, but since this is new, we don't know it. And we're going to do inverse norm. And the number I'm plugging in is 5% because I want to know what that number is on my curve. So we're going to go second vars, number 3, and the area is 0.05 for 5%. For y'all, please, 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 just stick to left. It just makes life easier because we're looking to the left, and we're going to hit enter. And my critical value here is negative 1.645. So let's go to our number, or our curve here. And put it in pink. I'm going to erase this because I don't have a whole lot of room. Negative 1.645. And if that's negative, then the other side is positive. We call that our critical value. That's actually our z-score right there. So if you need to recall for note-taking purposes, we did 0.05, and then our mean was 0, and our standard deviation was 1. And we colored to the left because it's a percentile. So that is my construction of my confidence interval. That's a lot, but hopefully that makes some sense. So number 11, let me move this for us.
Gotta get back into typing mode.
On number 11, it says interpret a confidence level to say that we are 95% confident is shorthand for what? So remember, when we're interpreting confidence levels in or if we were to repeat the sampling procedure, so let's do the cookie cutter response. If we were to repeat the sampling procedure many times, right? On average, always do on average, we're going to actually capture, we will capture the true, is it proportion we're dealing with? We'll assume it's a proportion. Proportion or mean in 95% of all samples. That's just a generic response because we're not actually interpreting, or we could say 95% of the intervals will capture the true proportion, and then we're supposed to do it in context. So if you want to use the actual verbiage that we did in class, we would say 95% of the intervals will capture the true proportion or mean. It depends on what we're dealing with, right? And then we have to do context. So ... Does the confidence level tell us the chance that a particular confidence interval captures the population? So confidence level never talks about one, right? It talks about all. So the answer for number 12 is heck no. This is not a probability for one.
Ms. Green and Mr. Washington, can you please stop by Ms. Ellison's office?
So we're going
Ms.
to
Green and Mr. Washington,
level
can you please stop by Ms. Ellison's office?
tells us about all possible intervals. Now, critical value, let's go back. critical value depends on how confident we are. So let's go back to number 10. That critical value of negative 1.645 and positive 1.645 is totally dependent on the percentile, like how confident I am. So we want to make sure we understand here that it depends on our confidence. Now, we're going to start talking about formulas on number 14. We're not quite ready to do too many mathematical calculations, but I do want to give you a formula. So I'm going to switch my laptop so I can write. Our formula is this. You're going to take your statistic. Now, what the heck is a statistic? It's what you observe in a sample. Whoops, I cannot spell. It's one number, what you observe in one sample. It's not your population, it's your sample. That's why I use S for statistic and sample. And then we're going to add and subtract, because remember we got two numbers in an interval. We got a low number and a high number. And we're going to add and subtract our margin of error. But our margin of error is our critical value times the standard deviation. What? That's a lot to think of, right? So this bad boy right here is our margin of error. And together, it's going to give us that math equation, or that little expression there is going to give us our actual interval. So let's take a look at we're almost done, 15 and 16. Why do we want high confidence in a small margin of error? Why do I want high confidence? Don't we want to be confident in our data? So high confidence tells us that our method almost always gives the correct answer. So high confidence tells us that our method almost, we like those squishy words, almost always gives us the correct answer. Don't we want to be confident? A small margin of error tells us that we have pinned down our parameter. Now remember, the parameters are population, PP, P parameter, P population, with precision. So there's not a whole lot of error. If you got low error and high confidence, that's gold. That's what we want, right? With precision. Let's see, explain the two conditions when the margin of error gets smaller. Because, folks, we want small margin of error, right? So here's the catch-22. When our level decreases, confidence level decreases. And you're like, wait a minute, if the confidence level is decreasing, isn't our confidence decreasing? But don't we want our confidence to increase? What? This isn't making sense. How do we do that? So it's tricky. So the only way our error goes down is if our interval, our confidence, gets smaller, right? Because we're getting closer to the center, the mean. The other thing that has to happen in order for error to go down is sample size. Hopefully you guys remember this from our lecture. Sample size has to get bigger. So there's less variability when your sample size gets bigger. So continuing with our discussion on Skinny pages 106 and 107, I want to take a look at the last two problems. Number 17 asks us to address the 3 conditions for constructing a confidence interval. So here's the bad news. We're going to have to check these conditions every single time. Do not ever give me a confidence interval or write down a confidence interval without actually checking that the conditions have been met. So the first condition, most important condition, is either random selection or random assignment. So random sampling must occur or random assignment must occur. Oops, I cannot spell today. And you must state how that took place. There's our lovely bell. Okay, so what's the difference between these two? So random sampling occurs when you have your entire population and you randomly select individuals from the entire population and everybody has an equal opportunity of being chosen. That's random sampling. Now, it's not always ethical to do random sampling because, like in experiments involving, medication or specific types of treatments, not everybody's going to want to be, selected for that experiment. So there are instances when random assignment takes place. So maybe you have volunteers say, okay, I'll be part of this study or this experiment, and they understand, the possible treatments that might take place, but then the treatments are randomly imposed. So that would be random assignment. One of those two random instances must take place. The next thing that must take place is we must have a normal distribution. So how do we check for that? Well, if we're lucky, we're told that it's already normal, but unfortunately, that's not always the case. So if we're not told that the distribution is already normal, we need to mathematically check for a normal distribution. And there are 2 ways to do this. There's one way for proportions, and there's a different way for means. So let me take out my pen, and I'm going to show you how to check for proportions. You don't do both, you do one or the other. So if you're dealing with proportions, you're going to first take N times P. Now remember, N is the size of my sample, and P is our proportion that we've been given. That's a given number. And we want to make sure that when we multiply those 2 numbers together, that they're at least 10. But you also have to do N times, well, let's just do 1 minus P. And that also has to be bigger than 10, or at least 10. That's for proportions. If it's means, ideally, we want to check CLT. Now, what the heck is CLT? CLT is the central limit theorem. And CLT tells us that as long as our sample size is at least 30, N is greater than or equal to 30. If your sample size is big enough, then the distribution, sampling distribution, is going to be normally distributed. Now you say, Mac, what happens when my sample is only size 20 or my sample is size 10? That's when you have to raise a red flag and say, is it ethical to even construct? I mean, does it even make sense to construct an interval? And we'll get into that in the future, but for right now, we're going to just leave it as this. And then the last one is, the last condition we must check is independence. You want to make sure your events are independent. One outcome has nothing to do with the other. And sometimes it just makes logical sense. Oh, this event has nothing to do with that event. And in that case, you can simply state that. If if you can't differentiate, if you don't know whether or not one has anything to do with the other, you can then take the size of your sample and multiply it by 10. If the sample size times 10 is less than your population size, we say that independence is satisfied. So what does that mean? Let's just take, for instance, Silver Bluff. Suppose Silver Bluff High School has a population equal to, we'll say 500 for right now, for easy numbers. And suppose I want to take a sample of size 10 from the population. No, let's not do 10 because we already have a 10. Let's say 12. Well, I would check for independence. 12 times 10 is 120, and 120 is less than my population of 500. So independence would be satisfied. However, on the flip side, suppose I wanted a sample of size 60. I wanted to talk to 60 kids at Silver Bluff. 60 times 10 is not less than my population of 500. So then I run into an independence concern. The events might not be independent, all right? So keep in mind, independence must be satisfied before you go and construct a confidence interval. And then, okay, last question. Almost done, guys. There are two things we got to remember when constructing an interval. Let's see here. Get my cursor over. Two things. Number one, you have to be mindful of the fact that the data has to come from an SRS. Our data should some random sampling has to occur. That's so important. It's like the most important thing. And then the other thing we have to be mindful of is error. Our margin of error only accounts for the error involved or from random sampling or random assignment. So margin of error only accounts for error that comes from random sampling, random assignment. There are other errors out there. Like there's undercoverage, for example. There's other types of things that can botch our interval. So margin of error only accounts for random sampling and random assignment errors, okay? So just keep that in mind. And I think that's it, folks. So hopefully you have a better understanding of communicating and understanding the parts of constructing intervals. And then in the upcoming lesson, we will learn how to actually create them. Hope this helps, guys, and I shall calculate later.